and post it on Moodle. I was trying to send out the notes for OneNote, and OneNote broke on me, so I can't get it shared. So I will post this video then. All right. DC mix and match. Again, this is going over everything that we've talked about this semester. All the different plans, all the different things are going to come into play to be able to solve this. So first thing that we need to know is, come on, step one. Our capacitor has fully charged and is an open to DC current. Step two, we're going to remove the diode and determine bias of the diode. Then we're going to determine diode voltage. Then we're going to use Kirchhoff's voltage law on the small loop. And that's going to determine our VR3, VR4, which then we can solve for VC to D. The next step is we're going to do a Kirchhoff voltage loop on the large loop, mostly to get VR2 and VR5. Then we can determine then we can solve for voltage of the capacitor, or VAB. And then 8, solve for VCD and VAB currents. So when we're done, we don't necessarily have to solve for the voltages for R1 or R6, but we could, if we wanted to, go the other direction for our VAB. Again, it doesn't really matter, those two things. So those are our 8 steps that we're going to follow. Okay, so step 1, step 2, I'm going to kind of combine together. So what we'll have, I'll go any further. Fine. So we will have our circuit that will look like this. We have our voltage source 1, we have R1, R6, we have point A and point B because it's going to be an open. We have R2 and R5. We have our other points here, which is C and D. We have our last 3 set of resistors, 3 and 4. And then our other voltage source. So we got 1, 2, 3, 4, 5, and 6. So 26 volts, 7 volts. We have 18 ohms, 33 ohms, 82 ohms, 20 ohms, 18 ohms, and 82. So now what we did, so this was step 1 and step 2. So we've treated the capacitor as an open, and we've removed the diode so we can find the voltage from C to D and then see how our diode is going to be affected by this. So when we do this, what we need to do is solve for our VR3 and VR4, because we're going to go from this point around to here. And find the voltages that we encompass. So our VC to D, and not the final one, but in this circuit, our VC to D is going to be the voltage of R3 minus 7 volts plus the voltage of R4. And to be able to find this, we need to solve for another value. So we need to find for our R total in this step. So our total is R1, R2, 3, 4, 5, and 6 all added together. So we have 18. Yes?
I got 253.
253?
Yep, that's what I got.
I think that sounds right, but we will just double check it.
Yeah, that's what I got as well.
Okay, sounds good to me.
I didn't know if you were waiting for someone to answer or not. So
Either or, if you guys get the answers, go ahead and shout them out. If not, I just assume I'm just going to lecture and you guys are taking notes. Okay, so this R total is in this case. What is our V total?
that would be V1 plus V2.
Yep, because how these will come across, series 80.
And then when they're like that, it's essentially, that's what connects it into series. If they were opposing, they would still be, they wouldn't be aiding, so they would be in series.
They'd still be series, but they'd be series opposing.
And you'd have to subtract the lower one out, right?
Correct.
It's
They would
dropping
have the
voltage.
Yes, yeah, because it's counteracting voltages coming into it.
That's what I was thinking, but I also wanted to make sure.
No,
Polarity is a tricky thing as well.
yeah, and not often do we have series opposing because it's kind of dumb. Why would you waste a battery in a circuit just to cut down on the voltage when you could turn the voltage down?
Yeah, no, that makes way more sense for sure.
Like a theoretical, I don't have a potentiometer, so I'm going to do the most expensive way of dropping.
Yeah.
Yes, exactly.
I'm going to go out of my way to make this work.
Mm-hmm. Sometimes that's what you have to do. Like, you have no other choice. Your boss told you to get this to work. They don't care how, just get it to work. Okay. Most of the time, those are not long-term fixes, though. Those are just get us through the week until we can get the part in.
Yeah, no, I was going to say, I imagine it's just until that part actually shows up.
All right, so we get a V total of 33 volts. So now I need to find out what the voltages across 3 and 4 are so I can look and see what this voltage of CD is going to do before we get into the biasing of the diode. So my VR3 is going to be equal to the 82 over 253 times 33, because it's just a series circuit, so we just can use voltage divider. And VR4 is the 20 over 253 times our 33. $82 divided by 253 times 33. We get 10.696 volts. We get 20 divided by the 253. And we get 2.609 volts. So then we're going to come back to our VCD formula that we solved for earlier. So we have a 10.696 volts minus 7 plus 2.609 volts. And so our VC to D is going to be equal to 6.305 volts.
That's the loop, right?
That's basically this loop going from C to D right here with the diode removed.
Okay, I just wanted to double check.
which is a different circuit than our main circuit. And again, we have to kind of do it to solve for it. So I have this voltage right now. So the next step is, once we have found our, so this is determining the bias of the diode. So now we need to put it back in and find out what the actual voltage is going to do. So I come back to my main circuit, and that's one of the problems with these is to keep track of everything. If you do multiple redraws, it does take some time, but it'll help you keep track of what is going on. So now we go back and we're going to put our diode back in. And looking from this point, we have from C to D, that means the positive is going down here because we came up positive. This is a 6.305 volts for our biasing, which means that we have positive voltage getting applied to this part of the diode right here. So now, when we look at that diode, with a positive voltage coming in from the top and being applied to the negative, the cathode of our Zener diode, what does it put that diode into? Does it put it into forward or reverse bias?
It'd be reverse bias.
Yes, because a positive voltage going into the negative side of the diode. What were you going to say, Madison?
I was going to say the same thing.
Okay.
Learned my lesson from yesterday.
No, you're good. So diode 1 is reverse bias. So now what we need to know is, now that it's reverse bias, now we got to look back at the characteristics that were given of the diode. So the diode, we're told, is a Zener diode, and it has a rating of 5 volts. So that means when the diode is in reverse bias, it will drop how much voltage?
5 volts.
5 volts. So what this is saying now, our V diode 1 is equal to 5 volts because we have enough voltage for it to be able to drop the full 5 volts. If this was under 5 volts, it would be dropping everything that it could to try and get to whatever it's rated for. But since there's an excess, it will only drop the 5 volts. So that means with our diode in circuit, it will have a voltage drop of 5 volts with the negative and the positive of the diode in this direction.
That's because it's reverse bias, right? Because it's like, since we were given the 5 volts.
Yes.
Okay.
If it were forward bias, it would only take away the 0.7 then, right?
Correct. Regardless of what diode it is, other than an LED. LEDs are special. They have, to get them to emit the light, they drop voltage based on what color they are.
The second semester, when you get into more LED stuff.
We will get touch base a little bit with them this semester, but really, LEDs you don't get into, I think, until about third, maybe third or fifth semester, just because that's when you actually start controlling them, and then you actually send signals to turn things on and off, and you use them sporadically throughout. There's no real one semester that you use just LEDs, but you can apply them in any of the different semesters if you really wanted to.
Okay, that's cool to know. Thank you.
One of the things like I've seen used before is like when you're programming and you're trying to debug your circuit live after you've uploaded the program to your chip. One of the things I would do is anytime it gets into a certain subroutine, I would have it turn on an LED or send power to a pin, which I would wire up for an LED. So I could see when it was in the main program, or I could see when it was in specific subroutines. And if it ever got out of the specific subroutine, I could tell if it was getting lost somewhere.
That's pretty cool.
It works great if you have the excess pins to do it. Sometimes it just takes up time, but when you're in development, that's what you're there for. You're trying to figure out all your bugs before you release it on your unsuspecting teacher.
So do we have to buy like an Arduino or something for that, or?
No, we actually have chips that you'll program to do that. And then a lot of times through third semester, it's more of hardwiring than actually programming chips. But fifth semester is all about programming chips. If you want to get an Arduino, then yes, you can absolutely do that. Okay, so we now know that the diode is in reverse bias and it has a 5-volt voltage across it. So now that takes care of step 3, or finishes up step 2 and takes care of step 3. So now what we need to do is we need to look at our circuit and we need to actually solve the values in each of the loops. So step 4 is the KVL of the small loop. So we write down our circuit again. And again, you don't have to write these down, but with all that we're going in, I'm trying to make sure that it's very split for what we're looking at. So we know the diode's polarity is negative to positive on the top, and it's got 5 volts across it. This guy is 7 volts. This guy was our 26 volts. And we had 183282. And then we had 201882. Okay, so now what we want to do is we want to find the voltages based on our small loop. So the small loop is just going to go in this area right here. And again, it doesn't matter which side you do first. I just like doing this one because there's less values to have to solve for. So again, we're going to do the Kirchhoff voltage loop. And we're going to start anywhere, and it doesn't matter, and we're going to follow in the direction of our loop. So the first thing we run into is a positive 5 volts across our diode. We're going to run into a positive VR3 because this negative is going to charge the resistance like this once it gets the voltage drop. This side will charge this side more positive, and we'll have the negative over here, just based on just this power supply it's connected to. So we'll have our VR3, we're going to have our minus 7 volts, and then a plus VR4, and that has to equal 0. So we end up with a negative 2 plus VR3 plus VR4 equals 0, and then the voltage drop of 3 added to the voltage drop of 4 has to equal to 2 volts. So what this means is there's 2 volts available for R3 and R4. Now again, since these guys are in series because we're just dealing with a loop, this voltage we can use in a voltage divider to see how it's going to split up. So when we're in this loop, the R total for, we'll say loop A, the first one that we did, is going to be equal to R3 plus R4, because that's all that's in this mini circuit, so to say. So we have 82 plus the 20, and that's going to give us a total of 102 ohms. So VR3 is going to be equal to 82 over the 102 multiplied by the 2 volts, because that's what's available, and we have to split that up. And then we just solve for that value. So we're going to have 1.608 volts. Now this value here is our final value because our diode is in the circuit, it's in play, we're taking it into account, and now we're just using Kirchhoff to solve for the rest of our voltages. So this is the voltage across R3. So 1.608 volts. VR4 is the next one we have to solve for. So that's going to be our 20 over the 102 times 2, or we take the 2, subtract the 1.608. Either way will give us the same answer. And then that is the voltage across R4.
I got a 392 millivolt.
That's it. Okay, so this takes care of step 4. So I'm going to shift this over. This is step 4 over here. We'll come back up here and look. So now we need to, so we did step 4. We've done 1, 2, 3, and 4. Step 5 now is solve for the voltage from C to D. So in this case, we have C here, D here. What is the voltage if we were to measure it? It would be the 5 volts, but in what polarity? Negative, because our positive is going to go, because we're saying go from C to D. So in our voltmeter, the positive probe goes here, and the negative probe goes here, and that's against the polarity of our diode.
Diode set the polarity.
Yes. So again, it's very important that -5 is what the actual voltage is going to read. So we don't quite have enough yet to solve for the current because we need to find the other voltages for 2 and 3 first, or 2 and 5, to see how it's going to split. But we'll solve that in the next loop. So here is step 5. And then the next step is we're going to solve step 6, which is we want to solve for the big loop. So the KVL of this guy. So again, I'm going to pick a point and go through my loop, and it doesn't really matter which direction we go. So I'm going to have a negative 26 volts plus my VR1 plus my VR2 minus 5 volts for my diode plus my VR5 plus VR6, and then all that has to be equal to 0. So here's where it gets a little bit confusing, because we're going to basically solve looking at everything, but 2 of the values we're not going to solve for because we don't care about them. We're just looking at their relationships to everything. So in this case, we have our negative 31 volts, so those voltages will combine together, is equal to plus VR1, VR2, VR5, and VR6. All that is equal to 0. We move our single values away, and we get VR1, VR2, VR5, and VR6, all is equal to 31 volts. So that means that we have to have a total of 31 volts being dropped across those 4 resistors, which, because of our loop, puts those 4 into series again. So now we have just a voltage divider between all of these resistors, which we can just use to solve for it. The only ones we really actually truly care about is VR2 and VR5, because with it, that will give us enough information to be able to solve for our VAB, as well as solving for current to give us the current through C to D. And we'll be able to solve the current through A to B as well. So the R total for loop B is going to be equal to R1, R2, R5, and R6 all added together. So what we have is we've got 18, 32, 18, and 82. So the R total for loop B is equal to 150 ohms. And then the ones we care about is the voltage of R2 and the voltage of R5. We can solve for R1 and R6, but we're not really going to be using them, so there's really no need to solve them at this point. So VR2 is going to be equal to the 32 ohms divided by the 150 multiplied by this 31, because this is what's available to all four of these resistors. And then for VR5, we're going to take the 18 over the 150 multiplied by our 31. So we get 32 over 150 times 31. And so we get a 6.613 volts. And on VR5, we get 3.72 volts. And again, those are the voltages of those two components. So 6.613 and 3.72 volts. Any questions so far? Okay. So now so that takes care of step 6, which is do our Kirchhoff voltage loop for the large loop. Step 7 is now we need to solve for the voltage from A to B. So that is going to be going from point A and wrapping all the way around to getting to point B. So our voltage from A to B is equal to the voltage of R2 minus the 5 volts from our diode plus the voltage of R5. So what we get is 6.613 minus 5 plus 3.72. And our final VAB comes out to be 5.333 volts. So that means when we come back and we plug our capacitor back into the circuit, it's going to have 5.333 volts across C1. So then the last parts we have to figure out is how much currents do we have everywhere, okay? How much current do we have going across our capacitor? DC current.
We definitely have to find out resistance, which I'm kind of speechless right now.
For the capacitor or for the diode?
The capacitor.
So remember, what does a capacitor do to DC? What does it act like?
It acts like an open when it's fully charged.
Okay, so the capacitor is fully charged at this point. How much current is flowing through that capacitor DC wise?
Well, there'd be none.
None.
Okay. Oh, because it's fully charged.
Yep, because it's fully charged. Because we're not asking about a specific point in time. We're just saying what, the circuit's been hooked up, it's going, it's like we connected it up in Tina. Okay? What voltage would we measure there? How much current would we have? Well, we'd have 0 current, but we'd have the 5.333 volts. And that's just voltage that then that capacitor stores. So if we were to take it out, that capacitor would retain the 5.33 volts until it was discharged, which can be discharged by going through any kind of resistive surface, such as somebody's arm. Just saying.
Yeah, I was going to say, I'm kind of skeptical about when we get back in the lab and actually touch one of these, because after Monday, finding out that they just don't discharge, I was like, oh yeah, no, that makes more sense too. Like, if you're to touch it after it's been loaded, it's probably going to discharge on your finger.
It will. And you'll get a shock, and it'll be funny. And I will laugh, and it'll probably make my day.
So, just couldn't we like clip a jumper wire from that to like a ground source before we pull it?
Oh yeah.
Discharge it?
Yes, that would discharge it.
Or lick it. Do either or,
You could lick it if you really wanted to. I mean, if you really wanted to, yeah, you could.
I don't know. I feel like offering money to see that. Just to see the physical reaction.
5 point extra credit if you lick a fully charged capacitor.
Oh no.
No.
It'd be hilarious to see this happen though.
It has happened before. I will tell you this though, depending on the material it is, like a regular capacitor, a ceramic capacitor works really good. They will maintain their charge a lot longer. Electrolytics are better for their capacitance, but they have internal leakage, so those electrolytic capacitors will actually dissipate because they leak across themselves at some point. But yeah, you can charge caps, and I'm not saying that when I was going through this program, I never charged up caps and threw them back in the bin. I would never do that because that's just wrong. They make an LED go really bright before it burns it up.
Before it goes boom.
Mm-hmm.
Is it like that one, what is it, Human Torch, scene in Fantastic Four, in the original one with, what is it, Chris Evans?
I think so.
Oh, the supernova?
Yeah.
Yeah, when he goes supernova.
Mm-hmm.
You went supernova! Yeah, his sister was so mad at him. Who was that? Jessica Alba.
Mm-hmm.
Yeah, that was a good one.
Still, I can imagine that, yeah, being that guy would not be a wise choice.
Yeah. All right, so last step we need to do is we need to be able to solve for the current going through C to D. So basically what we're looking at this point is we're going to have R2 and R3. We'll have our diode. And then we'll have R4 and R5 down here. So what we have is 32 and 6.613. R3 is 82 ohms and 1.608 volts. R4 is 20 ohms and 0.392 volts. And R5 is 18 ohms at 3.72 volts. So basically at this point, we're just looking at this part of the circuit, and I don't really care what everything else is because we've already taken into account. So now we just got to see what is our current doing. So now we're going to use our Kirchhoff's current law to solve for this guy. So current going into a node, going out of a node. So we need to solve for the 4 currents. So R2 is going to be the 6.613 divided by our 32 ohms. So we're going to have 206.656 milliamps. R3 is 1.608 volts divided by 82 ohms. So we have 19.61 milliamps. R5 is 3.72 volts divided by 18 ohms. And then R4 is 0.392 divided by 20. And we got our 19.6 milliamps. So which makes sense, okay? We have our 19.61 milliamps is going this direction. The 206 is coming in this way. We have current that's now going to split and go down through our diode. This 19 milliamps is going to continue because we've got a power supply, so it's going to make this corner and come back around. So R3 and R4 should be the same current. R2 and R5 should be the same current because these currents are going to come and meet back together. So basically what we want to find is how much current gets diverted and goes through our diode versus going around the whole way in the circuit.
Couldn't you just subtract your R2 current from R3?
Exactly.
Or with R3, should I say?
Yep. So what we end up with is our ICD is equal to 187.057 milliamps. Now remember, what was our voltage?
Around there?
Yeah, going through the capacitor.
5 volts.
Negative 5 volts. Our current's going to follow polarity.
So it'll be negative as well.
So it'll be negative as well. So there is our current through C to D, our voltage through C to D. The voltage from A to B was 5.333 volts, and the current from A to B was 0 amps. And we have our final values. Pretty painless, right? Lots of steps, but pretty painless.
Well, it helps when you break it up like that, because I was trying to solve everything all at once, not doing little loop versus big loop and just losing values.
Yep. Always, always, always try to break it up into small pieces. Okay, any questions about that? Okay, with that, let's take a break and we'll reconvene here in about 5-10 minutes. Sound good?
Yep.
Okay, we'll see you guys in a few minutes. nice outside.
It is really wonderful day.
I'm gonna take a walk around the building. I'm starting to walk up. That was a mistake.
Why?
I don't want to come back in. Walked out to the front and into the sun, and it was just like, oh, it was so nice. It was so beautiful. Oh. Let's see. Oh, let's see. All right, guys, welcome back. Where's my mouse? There's my mouse. Yay, it's a party. Woohoo! All right. What else would you guys like to go over?
Maybe a Thevenized circuit.
Okay.
Unknown R3 again would probably be the most easiest and simplest, I guess.
Okay.
We did a bridge yesterday and stuff, but just like to go through all the different types.
Okay, we can do that.
The extra little variable always makes me kind of question whether I'm know what I'm doing or not.
Right. Okay, let's do it. Oh, I guess, I should have ended the recording, but that's okay. It'll just make it for a long video. How about that? One video.
10-minute break.
Yeah, 10-minute break in the middle of the video.
Intermission.
I should have had some good music playing.
We could have put the intermission sign up to like the Godfather or something silly.
Yes. Or Monty Python or any of those.
Oh yeah.
That's what I should have done.
You could probably still cut it in.
Yeah, that would require
Now
more
we know.
work. Now we know. Next time I'll get that queued up we'll do that next
Yeah,
time.
next week, yeah.
Oh, now you're getting me ideas of crap to put up on the screen for next class.
I love that though. Like that's the spark that we all needed and enjoy.
All right, so we're given 50 volts. R1 is 3 kiloohms. R2 is 2.2 kiloohms. Let me make sure that the problem matches values. Okay. R3 is 4.7 kiloohms. 4 is 4.3 kiloohms, and R5 is 1.2 kiloohms. Okay, what we're looking for is R Thevenin in kiloohms, V Thevenin in volts, and the voltage itself across R3 in volts. So were you thinking this or the unknown R3 value?
I can't see what you're right.
Yeah, I wouldn't say that too.
Yeah, no, I can't give an honest answer. I can't honestly see it.
Fair enough.
Pi to the second power.
Pi to the second power. So were you thinking like the bridge circuit Thevenizing 3, or were you thinking with that unknown R3 value?
This one will definitely do 2 as well, but the unknown R3 was just something I'd thrown out there because we'd done one like this yesterday, so I guess we could Thevenize like a different resistor.
Well, it's up to you guys. If I can go through this one, or I can go through the other one, or I don't know if we'll have time to go through both of them, but it's honestly whichever one you would like to see.
This one would work great for sure because this one's definitely got a lot more going on in it.
Okay.
I already forgot the R7 redraw for this one. This one makes me angry.
That's what I mean. Like, there's so much more going on. The unknown R3 one, I've kind of broken down a little bit. It's really just about finding the values to subtract from each other. But
Yep.
as far as that goes, like this one's a whole other.
Okay.
Just to check real quick, with the R7, if you took out R3, be like R1 and R5 in parallel, R2 and R4 parallel?
Yes, and then you add them together.
I was right. Okay, that was my question.
Yep.
Thank you.
No problem. All right. So A and B. So we're going to take out R3 and solve for this guy. We're going to find out what the voltage is across it. So step one is remove the load. So we end up with is a circuit that looks like this. We got R1, R5, R2, R4. So R1, R2, R4, and R5. And then we have points A and B. So then what we need to find is our R Thevenin. So R Thevenin is equal to the resistance from points A to B. So our R Thevenin redraws, we start drawing with point A. Point A is connected to two resistors, R1 and R5. R1 and R5 are connected together. And then we're going to look at point B. Point B is connected to two different resistors, where we have R2 and R4. Those guys are connected together, but then they're also connected back up to R1 and R5. Through this wire here, remember when we short out our power supply, that becomes one wire.
That's usually the part that I always goof up on this redraw.
Yep, just remember, go slow and just connect, go one component at a time. What is connected to what? So the R Thevenin formula will be R1 parallel with R5 added in series to R2 in parallel with R4. So yes, Mary, you were exactly correct.
I was close. I thought R1 and R2 would be in series.
Oh yeah, no, R1, R5 are in parallel, R2 and R4 are in parallel, and then you add them together in series.
Okay, I knew I was doing something wrong. Anyway, thank you.
So we got a 3K in parallel with a 1.2K, and then that's going to be added to a 2.2K in parallel with a 4.3K. So we have 3,000 negative to the inverse plus the inverse of 1,200. Add those together, take the inverse of that, and we get 857,143. And then on the other side, we have the inverse of 2,200 added to the inverse of 4,300. And then we take the inverse of that, and we get 1455.4. We add those together, and we get an R Thevenin is equal to 2.313 kiloohms, which our units match up. Okay, then the next step is we need to find the V Thevenin. So this is going to be a good example of our V Thevenin circuit. So basically I'm looking from the voltage from point A to point B. So I'm going to go to point A, I'm going to walk down my circuit, where am I connected to, and then I'm going to choose a direction to go. In this case, I'm just going to go and wrap myself around this way and get back to point B. So my V Thevenin is going to be equal to the voltage drop of R5 plus the voltage drop of R4. Well, now we got to look and see what the polarities are. So current flowing from the positive to the negative is going to charge this guy positive, this guy negative, this guy positive, this guy negative, and then R2 is going to charge in the same polarities. So what happens is my voltage for R4 actually is a negative voltage. So I have VR5 minus VR4. And another way to look at it is I'm adding a negative VR4. So then to solve for this, because I'm still dealing with the circuit with our load resistor removed, now I'm going to use voltage divider to solve for the VR5, VR4, just like what we were doing in the last problem with the mix and match. So when it comes to VR5, I'm looking at that branch. And what I have is a 3 kilo ohm resistor and the 1.2 kilo ohm resistor in series, and they're in parallel with the total voltage. So I'm going to take the 1.2K, divide it by those two added together in series, multiplied by my 50. VR4 is going to be equal to the 4.3K over the 4.3K plus the 2.2K, because that's what's in series in this branch, and it has access to the same amount of voltage, so that'll be times 50.
You can solve them pretty much individually, each branch.
Yes.
Voltage then.
Yep, with that load resistor across A and B removed, yes, they are just two separate independent branches.
Okay. It just kind of becomes a parallel circuit.
So the first value comes out to be 14.286 volts. And VR4 turns out to be 33.077 volts. So we solve for VThevenin. So VThevenin is equal to 14.286 volts minus 33.077 volts. And our VThevenin comes out to be a negative 18.791 volts. So this is where the polarity becomes very, very, very important. So our VThevenin, like we said, is a negative voltage. So what that's going to do is it's basically going to change our circuit, our Thevenin circuit, from looking like this with our load, and it's going to turn into this. There's our R Thevenin, and then we have our negative to positive. And the only difference that that is going to do is this is going to give us a voltage across R3, which is going to give us a polarity like this. And all that means is that the R4 voltage is larger than the R5 voltage, but it also means that the R2 voltage is larger than the R1 voltage. So then to solve for our circuit, we put in our negative 18.791 volts. We have 2.313 kilo ohms for our R Thevenin. And then we put our load back into place, which is 4.7K. And now the only other question I need to know is what is the voltage across R3 actually? So with the circuit into play, it's going to redistribute it. So we're going to take this 18,791 and we're going to split it up between our R Thevenin and our load. So VR3 is equal to 4.7 kilo ohms over the 4.7K plus the 2.313K multiplied by the negative 18.791 volts. And we end up with, let's see, 4,700, 2313. So our VR3 is going to be negative 12.593 volts. And that is our answers.
Wild.
It just breaks down so simply. Sometimes the way you do it, I'm just like, what? The more, I mean, especially when I get to I can get the resistance Thevenin, but the V Thevenin, I'm just like, okay, voltage divider, I mean, I would have gotten a positive value somehow out of that. I don't know, but I probably would have.
It's because you would have taken it and you would have flipped that in your head when it comes to your V Thevenin.
It's nice to see when you do it, because when I do it on my own, I'm like, alright, got this. And then I'll like just doubt one step, and then I'm like, never mind.
The polarity is usually the step I doubt, and I'm just like, God.
Mm-hmm.
It's a mess after that.
That's a fair point. For me, it's usually just like how you do things.
Well, good. I'm glad. Not glad that you guys screw up, but glad that you understand. Sorry.
Well,
I thought you were gonna be like, good, I'm glad you're suffering.
in the way you explain it definitely helps break it down. It's a lot easier for us to understand. Is the way that I'm sitting here thinking about it. I'm like, okay, all right, yeah, no. So you would, because that is your A and your B. That, I mean, because I'm used to the notes, so.
Right.
Could you essentially pick VR1 and VR2 to find voltage, and then just, I mean, depending on the loop, I guess you win, but you can still kind of get the answer for your R5 to R4 if you just subtracted out what you got from R1.
To a point. The only problem is once we go through here, like this, the value that we got for R3 is the value for R3, but now the problem is we still don't know what the voltage is for R1 or R4. And you could do a Kirchhoff's voltage loop that would go up through your power supply, down through R1, across R3, down through R4, and then you could do voltage divider at that point, because then you're going to know your total voltage, just like what we were doing with the DC mix and match. So yes, you could. It just makes it so that it's not very easy to do.
Yeah, it makes it more complicated.
Mm-hmm. But it is definitely possible.
See, and I think for some reason my brain is just like, okay, that's the next step, and then it just gets.
Yep. Because in this case, we don't care what the other voltages are. We're just looking to see what it is across the bridge.
Just our load, okay.
Yep, just the load in this one. If we wanted to know all the voltages, yes, then we'd continue on from here and we could solve for it. Because yeah, we'd use Kirchhoff's loop to be able to go through a full loop to find the values, and then we could go through and solve for it using voltage divider, just like we did in the DC mix and match.
Especially if A and B were open.
Yep. Okay. Do you guys have any other questions?
I am good for now. I was gonna go and study and then hopefully take my test tomorrow morning.
Okay, sounds good.
But yeah, so another question is that, is there going to be classes of any sort tomorrow?
I wasn't planning on it, but if you guys have individual questions, please reach out and contact me.
Okay.
I was gonna kind of give you guys the day to be able to get everything done.
Okay, because I think if like there's everything pretty much being due tomorrow strictly, I don't know if arriving at class would be necessary, which I think that's
Yeah, if you have specific questions, feel free and reach out, and I'll answer. But I don't know if I won't have the Zoom calls and stuff going.
okay.
And then since we're here, Monday we show up in lab like normal.
Yep, Monday will be normal day, and I'll make sure I send out an email over the weekend before Monday that says, "Hey, remember we're meeting in class on Monday."
Cool, very cool. Last 2 weeks sucked.
It is rough, but
I need that. I need to be there.
yes,
People that just can't. I don't. I can get through with it. It's just really rough for me. And then yeah, the last couple weeks on personal notes have just been rough. So being here is just twice as rough.
mm-hmm.
Same here. I have to be there in person and just I guess it's just kind of like there's just life around you that's just learning as well. You know, it's just like when you're in your own room or whatever, just looking through a computer screen and just trying to learn it online. It just doesn't feel alive or something like that. You know what I mean?
Exactly.
It doesn't sink in as hard. I feel, and that's my thing. Like I have to go back and recheck, and then I start doubting what I did learn to begin with. Like Mary was saying, like there's just sometimes where I just start doubting myself after a minute or two, and I'm like, why?
Yeah. Okay.